diseases in medical fields. Affymetrix, Celera, Genentech, very famous company with a long history, Genome, Interpreting Genome project, and Illumina, a very highly developed company and very fast developing technologies and equipment. Some time ago, we had a very pleasant meeting with Spiral Genetics company representatives, and this is the startup in Seattle, USA. Their focus is to make work of bioinformatician simpler. So mentioned formats of genome information is uploaded to the server, which is located anywhere in the world, because Amazon technology, cloud technology, helps us to upload the information on any server which is preferred in this country. For example, Russian companies do not like to store their data in the US border. So this company offers Singapore, Western Europe, and even Russia servers for making cloud computing. So the data is protected quite strictly. And this technology and this approach makes us happy for waiting to make interpretation of genome more with higher usability. It means that these huge text data is converted to something more visible and more with more potential for use in clinics. Because our infinite goal is to treat the broken gene with gene therapy. There are several labs in the world concerning gene therapy, and we are collaborating as a partly clinical company with experts in Italy, Germany, UK, Japan, and US for sending our patients with found mutations for treatment in the certain lab which focus of research is in that field which patient have a disease, for example, glaucoma or retinal dystrophy or some other diseases. Decode is a very important market company which was obtained by MGene several months ago. This company is located in US, and it is a very interesting and thorough company interpreting the rare genetic disorders, because in the scale of a country, the number of patients may be not enough for researching the disease. So as soon as we have, the world is developing nowadays, and we have hope for interpreting data from all the globe, from all 6 or 7 billion people. So that is our hope for personalized medicine. When rare diseases, they are called orphan diseases, also can be treated thanks to cloud technology and internet availability over the world. So GeneDx is very good with these rare diseases. This is a technology company, Life Technologies. A lot of equipment is imported to Russia, this company. And this is an example of a team which investigates a very complicated disease, not monogenic, but multifactorial disease like age-related macular degeneration. So this is the retina degeneration leading to blindness, which is not the reason for what is very difficult to find, because there are hundreds of factors, and only with mutual efforts combining GWAS, genome-wide association studies, we can find, and linkage analysis, we can find factors which influence on the progression of the disease and in the end the treatment of the disease. So what we can tell about intellectual properties? Please tell me, anyone, does anybody have an experience protecting intellectual property in biotechnology?
Not yet. You have?
Yeah. Trying to protect.
Positive experience?
No.
Could you please outline the major factors which were difficult to... What was the first impression of that memory?
That the patent examiners don't have a clue what they're doing and can't read the description that you have sent them, and then they find a whole lot of prior art that is totally different from what you're talking about, but they don't have enough knowledge to discern between the art.
Not enough competence in determining the issue, the main thought of patent, right?
Yes.
Of intellectual property.
Yeah, the subject.
So I think it's a whole world task and challenge to increase the communication between people, because information is bursting around, and in majority of cases, information which is the basis for technology, information is so huge and spread away, and it is very hard to focus and to spread it, useful information, to gather it, and throw away all the rubbish, all the junk information. So as we faced with intellectual property challenges in Russia also, because in Russia we have patent system in Russia, but if you want to be a global player, global market player, you have to protect your intellectual property in the international field, and also in US patent system. So with a certain kind of experience, you can be successful in patenting, in protecting algorithms and oligonucleotides, which are extremely important in your testing technologies. So the slide which excites me most is that these days it is really not so important where in the world you are located, and that makes me happy, because only one step, sending your biomaterial, for example blood, to the technology company, is the only chain which depends on your location. So after your sample is being received to the laboratory and sequenced, processed, and stored, saved, you can analyze it once and again and again and again, so you can use it multiple times, many times. And the good thing is that technology is being developed, and data you could not use 2 years ago may be analyzed again, and completely different results may be obtained thanks to new technology burst. So analysis and interpretation via cloud computing is a very important achievement of humankind. So the results can be sent by email or any other kind of mail. What, in my opinion, is very important in regulatory affairs, and what I see in Russia, is a necessity of close cooperation and joint legislation in creating genetic two sides, government and biotechnology community in DNA testing. And only in association of experts can be created the system which is viable, which is sustainable in the political and economic climate of a certain country. Also, in Russia we have a challenge of biomaterial sending, because it is prohibited to send blood samples to other countries. So we have to send libraries, and that makes our processes much more complicated. Also, regulatory affairs should think about team location and the borders of international team process. Sometimes it is very hard to find a specialist in your own country, and when you find a foreigner, that can be not so easy to prove that you really need only this one person. So communication between team, programmers, bioinformaticians, physicians, researchers and managers is very important for the success of the whole project. And in the end, social and ethic questions are very important before beginning gene therapy wide experiments, because some preliminary successes of gene therapy are obvious, and there are several fantastic films, films of fantasy, which are, for example, Gattaca, where genetics is shown as a major disaster of humanity, and where people with changed genes are not, there is a conflict between gene modified people and originally how do you say?
Nature.
How do you say?
Nature people.
Yes, and nature people. So this issue is also very important, and I think the colors in that fantastic films are too dramatic, and in real life we can not have so sharp edges and conflicts. But certainly we have to improve legislation and to see the interests, to predict the interests of all the sides in this process, because it is containing our future generation. I have some more material about technology, about intellectual property, and some business processes, but I want to leave dialogue, so if you have any comments, I will appreciate, and thank you for your attention.
I have one question.
Yes, please.
Do you know how many people are suffering from ophthalmic disorders in Russia, especially which is connected genetic disorders?
I have only an approximate figures, but I think it is quite a lot.
Quite a lot.
It means that it depends on what disease do we take. If it is myopia, it is 20-25% of the whole world.
Mm-hmm.
So 20-25% of all Russians. If we take into account only serious eye diseases like glaucoma leading to blindness, retinal dystrophy, and amblyopia, it is with glaucoma approximately 3-4 million people in Russia, and about 10% of them are possibly can be corrected with gene therapy. So,
and what kind of percent of this number you can help?
10%.
10%.
Yes,
10%.
approximately 10%.
10%. And depends on?
It depends on genes, on technology, and if
the level of disorders.
Yes, and the level
Stage.
of damage of genes.
Yeah, sure. Thanks.
Thank you.
This 10% number, where does that come from? Is that the number of people that you have detected with a specific gene dysfunction, or is that actual capability of repair? Have you actually demonstrated that 10% can be improved with this therapy?
This is an average data. In our experience, it is approximately 10% also. But we base on statistical data, and for example, for glaucoma, it is a multifactorial disease, and 10% of it is caused by gene mutation, and I can show you the genetics of glaucoma. will have an initial information of what is it. Let me see, where is it? Yeah. So this is an initial find of a list of glaucoma genes. So for 7 of them, the treatment is coming. For 3 of them, the treatment is already here. And this is not the full list of glaucoma, of genes involved in developing glaucoma. So approximately 8–10% of people contain mutations in these genes.
Okay, so if we take one receptor, the very first one, the gene the AGTR2, angiotensin 2 type, or angiotensin 2 type 2 receptor, presumably you are basing your data on a sample of blood from an individual at one point in time, and then put into a database and merged with a sample of data from one individual. Have you ever taken one individual and sequentially sampled their genome to make sure that it is a mutation? Are you sure that that SNP that you're seeing is a mutation and not just and not just a temporary artifact in their genome?
I see. To say if it is a mutation or not, we have to check minimum 500 samples, right?
No, you should check it from one individual. You're checking from 500 individuals, and you're saying that it's a mutation because it's common to the measurements that you've made 500 times. But that's only 10% of the total sample. You see what I'm getting at?
Yes.
You
so
should
we
really
have,
be...
we check 500 people, and they have 450 of them have one sequence, right? 50 of them have another kind of sequence, right? And we cannot say if this is a mutation in these 50 people, because it can be the rarely seen LL in the nation. Did I get your question right?
No, you didn't get it right. The problem is, you are saying that a person has a mutation in their gene based on a single measurement at a single point in time of that person's genome.
I see. You mean we have to check several...
Serially. You should be checking serially because the genome may...
cells, right? Several tissues of a person.
Well, not necessarily, but you should certainly sample multiple times from each person before you assume that that SNP is going to be constant with time.
As far as I know, minimum 20 points of the genome is checked for making sure if this mutation is common to this person or not, if we take into account a blood sample, right? So do you think 20 blood cells is enough for making...
20 blood samples over a period of a month is probably enough.
As far as I know, Craig Venter was talking about it, that he had sequenced his genome several times, as he is one of the founders of this technique.
And it changed every time.
Yes, and that
That's
makes
what
the
I'm
market even more attractive, because it doesn't mean that you sequence your genome just once and you have all the data.
Well, it could mean that your whole hypothesis is incorrect.
But it is the best I know for this day. I can sit in the corner and cry, oh my God, it doesn't work. But it doesn't work. We have to move, right? And
we have to
that
understand.
is why I'm talking right here, to receive your feedback also. And I'm very glad you realize it. But again, it is not the reason for sitting.
Well, we actually wrote the chapter for Craig Venter's book, or the JCVI book on the metagenomics. We wrote the chapter on autoimmune disease. So we know pretty well what's going on out there. And that's why I was asking. It's a difficult question. It was a trick question. I'm sorry, but I just wanted to point out, and as you have done, Craig Venter's genome has been sequenced multiple times, and it was different each time. And we have to understand why it was different.
Exactly. Yeah. Thank you so much. And I think this also concerns legal questions, because we test the patient. We have found mutation. We say, oh, you have a disease, and we do not leave ourselves a chance to say, we will check you in 3 years, and we may not find this
exactly.
And at the same time, if we check a sample and find the mutation, and after 3 years we do not find a mutation, this deteriorates the faith in the genetic companies, because they say, oh my God, what we were doing, you were lying to us, or you were not processing the sample, or there are some kind of trust questions. So it's a long road.
It needs
Thank you so
confirmation, yeah, sure.
Yeah. Yes.
Yes.
Do you have any questions? Some more questions? Thank you so much for your attention.
Perfect report.
It is a very great pleasure to talk to you.
Okay. Thank you.
Yes, thank you.
Finish?
Yes.
Very, very difficult topic.
Yeah, sure.
Yes.
Very difficult topic for discussion.